Hi everyone, welcome to the iolite imaging webinar. Thanks for joining us. Today we're going to be covering all the new features in iolite, including all the cool new imaging features that we've added recently. Oh, sorry, I should introduce myself first. My name is Bence for those of you who haven't met me before, and Joe Petrus will be helping me today. He'll be co-hosting. I just wanted to mention that we are going to be using iolite version 4.3.5.1. That's quite a few version numbers there. The 0.1 version just came out just in the last few days. If you're not using that, then you can either update during the first 20 minutes or so of the workshop, because there'll be some presentation which isn't interactive at the start. Or you can just use version 4.3.5 because there's only minor differences between the two. It's a few bug fixes and stuff that Joe did between the last webinar and this one. And also, if you haven't downloaded the example datasets, feel free to download those. We'll be playing around with those after the initial presentation part. So just to let you know, we won't be covering the basics in this webinar. They're all covered in the basics webinar. So hopefully you're familiar with importing data, creating selections, and running a DRS. If you're not, for imaging, these things are pretty basic, but we do recommend you check out that the recording of that webinar if you haven't seen it before. So as I mentioned, today we'll start off with talking about some of the basics of collecting image data. For those of you who have been collecting image data for years, then this will be very basic for you, but maybe there'll be one or two items in there that might spark some interest, and maybe some discussion if you have different views than us. So we'll be looking at some factors to consider. So the reason why we bring this up is that quite often decisions you make when you're setting up your experiment will affect how you process things in iolite. And so we're trying to sort of bring those up before you even get to iolite, because you can't change how you've measured an image once it's already measured. So we will be talking about the different approaches to imaging, the simple traditional imaging, where you just set up a bunch of scan lines, and CellSpace imaging. We won't be covering 3D imaging in this webinar, but that's something that we are working on, and we'll definitely be looking at in the future. And then once we've done that, we'll be looking at iolite's imaging interface, and we'll be looking at how we can do some image analysis with regions of interest and profiles. And then we'll also talk about how to get your data out of iolite and potentially into other software or ready for publication. And at the end, we'll probably have some time, we'll almost definitely have some time for some questions and answers. So just in terms of the example data, so unlike the previous webinars where we've gone through step by step how to put together a session, this time we've got some sessions there pretty much ready to go, and you're free to just play with them. Just so if we're demonstrating how to, for example, create a profile across an image, just bring up one of those experiments, create some images, and start plotting a profile, and then you'll be able to follow along in that way. So it's not like a set number of steps to do things. And if you do completely mess up one of the session files, just don't save it and reopen it, and you should be good to go. So there are 3 different data sets. There's a Titanite one, which has got the file name .ttn.io4. This is a very typical image by selections, a bunch of scan lines all aligned. It's what most people think of when they think of LAIS and PMS imaging. We also have the original CellSpace example from the paper back in 2012, still loads in iolite 4. That's the otolith.io4 file. And we have another one in there that we were going to present on, but in the end, it doesn't, we decided not to include it in the webinar, but it's still there for you to try out. you can actually process it either by selections or by CellSpace. It's one of the few cases where you can do either. So just to cover some of the basics and some of the concepts that we will be talking about today, we'll just spend a little bit of time talking about factors to consider even before you get to iolite. So most people would think of an imaging experiment that looks something like this, where we have a bunch of scan lines. In this case, they're going from left to right in the X, going along the X axis. And we have a bunch of overlapping spots, and we have a bunch of scan lines which give us our resolution in the y-axis. So that's a pretty basic setup that can be flipped so that your scan lines are running from up to down or down to up. But just while we're presenting these concepts, we'll talk about scan lines running in the x-axis, and we'll be having scan lines stacked in the y-axis. This is what that sort of experiment would look like in time series. So we have a bunch of calibration materials run first, so just scan lines on each of those. And then we have the scan lines on our sample, and you can see that the scan lines have varying degrees of concentrations or varying counts as they go over different phases. And then we have some more calibration materials run at the end. You can also run calibration materials during your experiment. We recommend about every half hour to keep a handle on how your sensitivity drift is going. That will give you less drift across your images, and all that's totally possible with iolite. So in terms of setting up your experiment, some things that you might want to consider optimizing all come down to you're trying to maximize the amount of detail you can in the time that you've got. So if we all had infinite time and infinite money, we would just measure everything pixel by pixel in excruciating detail. But that's not possible, so we have to make some trade-offs. So basically, time is normally the limiting factor. And then after that, it's about sensitivity for a particular element of interest. So given that time is going to be probably our biggest factor, then you want to normally then start to make trade-offs with the following factors. So the biggest one being the concentration of the elements of interest. So this will affect everything from your spot size, like you may not be able to decrease your spot size beyond a certain amount because you just won't get enough material ablated, through to dwell times as well. So you can't have that depending on your concentration, you will have to adjust your dwell times. So to get the maximum resolution, you want the smallest possible spot size, the maximum number of scan lines, and the slowest practical scan speed, without being too slow, which we'll come back to in just a sec. Just before we get into too much more of this, I thought I'd bring up the idea of fast cells versus normal cells. So fast cells are now becoming more and more prevalent on the market. They do provide resolution on the scale of individual laser pulses. So that's really impressive and amazing, which does actually then bring up some issues for how we process images. In the past, we've sort of been using this steady state stream approach, which is where you fire the laser. If you were to fire the laser on a standard glass, you'd get pretty much a standard steady state signal. Whereas with these fast spots, they wash in and out so fast that we don't have a steady signal. And so that requires a different way of thinking about how we actually process it. And that's something that we're working on. Other people are working on it as well. Time will tell, I think, on which approach is best, but it's not what we'll be covering today in today's workshop. With the current steady state stream approach, you do get some effect from previous spots over your following spots, but there are ways to avoid that, or to minimize that at least. So just to show you the difference between a fast washout cell and a typical cell, on the left here we have some data from a fast washout cell. This is for the same elements on the same mass spectrometer. And you can see on the right here, we have a pretty typical cell with a washout time of around about 0.8 seconds. And its maximum peak height gets around to about 300,000. If you compare that to the fast washout cell, pretty much it's all washed out within the first 0.2 seconds. So this would all be crammed into this part here on the right-hand side. And also the magnet, it's three orders of magnitude greater, sorry, 2 orders of magnitude greater. So this is up to 12 million counts for the same and pretty much the same conditions. So we can see that we get much higher signals crammed into a much smaller time period. There is all sorts of interesting internal structure depending on what fast cell you're using. I think all 3 different the 3 major laser instrument manufacturers have different approaches. So there's going to be differences in these peak shapes, but it's quite interesting, and it's something that we're working on at the moment. But just to let you know, pretty much we're talking about traditional cells, typical cells, for the rest of this webinar. So if we're looking at this sort of setup here, where we have scanning across in the x-axis, and we have a bunch of scan lines in the y-axis, what we can see is that the total image time will be determined by our resolution in the y-axis, so how many scan lines we have, and how fast we're scanning, so how long it takes to do a scan line. And the resolution, so the resolution, that's the y-axis part. And what we end up with here is that the x resolution is determined by the mass spec sweep time and the scan speed and how far you're scanning. Whereas in the y-axis, it's determined by the number of scan lines and your spot size. The effect of this is that we end up having very different resolutions. So we normally have thousands and thousands of data points in the x-axis, and normally tens to maybe 100 or so in the y-axis. Just to look at some of the other parts from the laser perspective, obviously we're using pulsed UV lasers, so you want to take into account your spot size, and the spot size affects the resolution that you can go down to because it affects the amount of actual ablated material. It's different from sample to sample and from lab to lab, from laser to laser, but you want to use the smallest practical spot size to provide sufficient counts for all elements of interest. And by sufficient, I mean that that is entirely dependent on what sort of experiment that you're doing. You also want to optimize the repetition rate. So this changes depending on sample type. So for biological samples, you might only get 5 to 10 pulses before you've actually burnt through the material, and then your ablating slide. Whereas for silicates, you can tend to get a lot more pulses on them. We tend to use in our lab between 5 to 10 hertz usually. If you go much faster than that without moving faster, then you can actually start to get sampling in the z-axis as well. And so just as a footnote to this sufficient note here is that it's entirely application dependent. You might be using limits of quantitation, which is 10 times the background noise, or less if you just want to know high versus low. So it really depends on what you're trying to achieve. You also want to optimize laser power. This isn't done normally for every experiment, but just showing a figure here from Ziegler et al. From 2003. This is some simulation data where they showed that you have normal ablation, what I'll call normal ablation, with increasing fluence, and this is basically the number of counts that you'd get for that, until you increase the power to too much, and you basically start getting melting effects, and that's when you get a big jump in the number of counts that you would get, because you're starting to get melt droplets and all sorts of thermal effects. And generally we want to avoid that. So not always more counts is better. You want to probably stay in the ablation zone rather than the melting zone. It's something, It's something that's probably worth trying out if you're trying a different matrix. If you're working with sulfides, it's definitely something to be aware of, but for things like biological samples, then you probably don't have to worry too much about the thermal melting type effects. And the scan speed, the raster rate, this determines how long it takes to scan each scan line. And if you scan relatively slower at a fixed rep rate, you get more spots per area. It also means you get more mass spectrometer measurements per area, so that you don't then just have one measurement for your spot area, but quite often for some of our experiments, we have up to 5 measurements for a particular spot area. And this actually gives you increased statistical precision, but it also increases your total analytical time. And just a note about the Y resolution. So this is sometimes something that is overlooked in favor of optimizing everything for the X-axis. This is just, it's not a laser ablation image, it's an SEM image of a little tardigrade, these cool little animal type things that can live just about anywhere. Here's the original image, and in each case I haven't changed the X resolution at all. But I've downsampled it so that there's only 30 scan lines in this image, and downsampled it so that there's only 10 scan lines in this image. So if this was our feature that we were trying to look at, you can see that if we only had 10 scan lines across that feature, then it would be very, very blurry. By the time we get to 30 scan lines, we're starting to get an okay image. So just as a sort of rule of thumb, you probably want about 30 scan lines over your area of interest to be able to resolve the features. So hopefully that helps. Also, just a note about the laser spots shape. Initially, we did everything with circles. This was based probably from our spot analyses. And in fact, in the CellSpace example that we're using today, we were still using circles at that time. The problem with using circles is that the outer part of the track only gets one pulse, whereas the center of the track gets multiple pulses, and you end up with a track profile that looks something like this sort of curved profile. And it means that you're not sampling evenly over your track profile. That's why we recommend square spots, so that you end up with a track profile that looks like this. Where the spots overlap, you will get more ablation, but at least it's a more representative sampling of your spot line than using a circular spot. So that's all the laser things that you might want to take into consideration. If we now have a quick look at the mass spec options that you want to optimize, probably the most important one of those is taking into effect that we're dealing with a sequential detector. I'm talking about quads here. If we're talking about simultaneous detection, so multi-collectors, then it's a different setup, but I'd say 99% of imaging is done by quad. So with a sequential detector, you'll be aware that each mass is measured just for a certain amount of time. For today, we'll call that the dwell time. Certain mass spectrometers sometimes call it something else. And between each dwell, there is a settling time normally, sometimes called an equilibration time. And this is where the mass spec is not actually counting data because it's in a state of flux. So we'll call that settling time. And the total amount of time it takes to measure all the masses, including all the settling times, we'll call the sweep time. So just down here, we have an example where we have the mass spec is moving to a certain mass. So it has it has some settling time, then it's measuring mass 1, then it moves to mass 2, it takes a little time to settle, and then measures mass 2, and so on. And in this case, we only have 4 masses, but the total time to measure all 4 masses would be called the sweep time. So in this case, we want to optimize, in most experiments, you want to optimize this dwell time. So if you have elements that have a lot more abundance, then you'll count more ions within a certain amount of time. So you want to decrease those as much as possible, because the longer your total sweep time, the less resolution you have. If, for example, you're scanning with a 50 micron spot and your scan speed is 50 microns per second, then you want to have a sweep time that's less than 1 second, because otherwise you'll start to be still measuring from the previous spot area when you move along. So as I mentioned, if you have sufficient counts for oil elements of interest, you want to start decreasing your dwell times so that you can actually measure faster, or you can measure a larger area. You should also take into consideration your pulse width too. So if it's going to take 8.8 seconds to wash out, then you want to make sure that you're not moving so fast that, even if you have 100 measurements across that, the material is still going to be coming out 0.8 seconds later anyway. One thing to take into account with this decreasing your dwell times is duty cycle. So duty cycle is the amount of time that you actually spend collecting data relative to the sweep time. So if we were to look at this example, if we said that each one of these settling times was 1 millisecond and each dwell time was 3 milliseconds, so then total amount of actual dwelling in this would be 12 milliseconds, and the total time would be 16 milliseconds. So we'd have a duty cycle of about 75%. Typically, we don't want to go below about 80% for a duty cycle, and because what you want to do is you want to avoid this sort of situation. So if we really decreased our dwell times down by heaps, we could have something that looks like this, where we have only about 25% of the time we're actually measuring our ions, and the rest of the time is settling time. And so in this case, it'd be around about a duty cycle of about 25%. So you're throwing away 75% of your sample. You're just not measuring them. So there's only so far you can go down in your dwell times without starting to throw away data. So they're some concepts you might want to think about for the mass spec side of things. And then with actually measuring your samples, you want to obviously try and matrix match your samples to your reference materials. This helps to correct for effects like matrix effects. So that's to do with ablating different amounts of material per spot. Also can take into account condensation effects and plasma loading effects as well. So obviously, it's best to match your reference material as closely as you can to your sample. If you can only get so close, then you can do other things like normalization. So that is all sort of the analytical side of things before you even choose what style of imaging you want to do. When you actually set out your experiment and you start putting scan lines in, you've got some choices, and basically you can choose between imaging by selections, the traditional approach, or by using a CellSpace approach. The imaging by selections is the easiest to set up. It's just putting a bunch of scan lines onto your sample, but it is slower to measure depending on what shape your sample is. And you do potentially spend more time measuring just background material. CellSpace imaging, in contrast, is the idea that if the mass spec is recording composition versus time, so we have a time for every mass spec measurement, and the laser log file is recording the sampling position versus time, as well as the spot size and a bunch of other things. If we synchronize those two records, then we end up with composition versus sampling position. So we know the XY position and the composition at that XY position. So why would we use this approach? Well, it saves a significant amount of time. It means you don't have to measure a whole bunch of background that you didn't want to. It means that you can overlay your laser ablation data onto other registered images, which gives you some context and produces some quite interesting images. And it does give you this spatial averaging rather than temporal averaging. So when you do everything by selections, you're just assuming time is equivalent to space, whereas with CellSpace, you can actually see where spots overlap. And also, it does potentially represent the spot as it actually looks. So if you're, for example, using an extended slit, so a very elongate rectangle, or if you're using something other than just a rectangular pixel or a circular spot, if that's what you're using, it will be faithfully represented as such in your images. And we'll see that in the CellSpace example, where you can actually see the circular spot shape. So we put this out in 2012. There's paper there if you want to go check out some more details about how it's done. But just to show that in another way, so if on the left-hand side, we have our mass spec data, which is recording time and composition. I'm just showing one channel here. So this is calcium counts per second, representing the calcium composition. And in our laser log file, we also have the time and the sampling position. If we synchronize the two times, we can actually end up with the sampling position and the composition at that sampling position. So knowing the spot XY and the spot size and shape, we can then start to plot it. And the way that looks is if we were to draw up a pixel grid like this, and we knew our spot was centered about here, and if it was a circular spot, this has been quite heavily pixelated just because we didn't want to put in too many pixels so that you couldn't see what was going on. It would look like this. So if the mass spectrometer, while the laser was sampling here, it said that the concentration was 5, we'd fill all these pixels with 5. And then for the next measurement, we know that the XY position center of the spot was here. So we fill all this area with 7s. But you can see that because the spots are overlapping, the 7s with the 5s, there'll be some area here with some 6s. And then if the next spot moving along we had a composition of say 30, and the XY center was here, we'd fill the pixel grid with 30s, and you can see where they overlap, it's taking that into account. So it's important to note with this that we're not measuring every pulse, we're actually plotting every mass spectrometer measurement. So this is not each laser pulse, it's each mass spectrometer measurement and where it was measured. And it does give this spatial averaging. So, we would get something looking like this for temporal averaging, but if we have spots that are overlapping along their sides, we also get that as well. There are some implications for the statistical analysis of the images later on when we talk about pixel grids, where for each spot we have more than one pixel, but we'll come back to that later on because Joe came up with a really great way of getting around that. I also mentioned that you can add some context to your images by loading coordinated images. These days, I think all the laser control software allows you to import an image and transform it so that it's in the same coordinates as your cell. And then you can export those images that you can then import into iolite. These are usually called either registered images or coordinated images. And once they're registered, they normally come with a .coord file. And this is just a text file, and it just has some information in there about your image. So normally pieces of information that iolite need is the width and height in cell coordinates, and the top left position of the image. So with those bits of information, we can then plot the registered image also in our cell coordinates. So as I mentioned, we do have this example, this otolith example. So for those of you who have never come across otoliths before, they're the bony part of a fish's ear. They start growing, and in this case, it would have started growing about here. And then every day, another layer is added to the outside. So they expand outwards like tree rings. And the chemistry of the otoliths, which are, I think they're basically aragonite, I think. They're basically calcium carbonate, but their chemistry reflects the chemical conditions of the water that they were in at the time. So people studying these can use for example, the strontium isotopes to work out if they're in fresh water or salt water. They can also use the trace element contents to work out the same sort of thing, whether they were high or low in the water column, those sorts of things. So they can use them for managing fish stocks, working out where fish breed, those sorts of things. So as you can see, if we had measured this by normal, traditional imaging, we would have had to set up a bunch of scan lines going across, right the way across, or maybe we'd do big long scan lines from top to bottom. But with CellSpace imaging, we can actually just put scan lines over the actual image, because the scan lines can be any length they want. Each individual one can be any length that it wants, and they don't have to be aligned in any way. So for traditional imaging, your scan lines need to be aligned either on their left or their right or their centers. But for CellSpace, there's no requirement for that at all. So it actually means that we don't have to measure all these background areas. Out here, for example, there would have been a whole heap of background, and over here, there would have been a whole heap of background. So potentially it cuts down your measuring time by 30%, depending on your image size and shape. So that's kind of the background information we wanted to talk to you about before you even get to iolite, because if you've decided to measure your images by CellSpace and by selections, and then later on you decide you want to do it by CellSpace, you need to have made those decisions right at the start of your imaging experiment. But now that you have measured some data, let's say, and you're ready to look at it in iolite, this is the basic process that you would do. So for the first part of the processing your experiment, it'd be exactly the same as any other experiment. So you'd import your data, you'd create some selections for your baselines, reference materials, and your samples, and then you'd calculate some results using a DRS. And then you would check those results, maybe using secondary reference materials just to make sure they make sense. And then you would move on to creating your images. So just as a way of looking at that, let's have a look at the tight night experiment. So I'm actually going to process it from the start. If you open the ttn.io4 file, you'll see that the mass spec file is already loaded, and the laser log file is already loaded. And if you look in time series, you'll be able to see that we have some baselines down the bottom here. We have some NIST 610, which was the primary reference material, some measurements of that, some scan lines of that, about every half hour. And then we have a bunch of scan lines going across it. But just to show you how easy that is to set up, I'll just create a new session. And I'm going to import a TTN file. It's a X series file. And I'm not going to worry about the dwell times in this case. I'm also going to import the laser log file, which is the TTN map log. So you will have these raw data files as well. You should get an offset of about 113 seconds. And then we're going to, I'm just going to pull this. Then we're going to use the automatic setup in iolite. So I'm going to select everything, click auto selections, and it's going to automatically put everything into the right groups for me. And it's also going to create baselines for me. So trimming back 15 seconds and having a duration each time of 14 seconds. And click OK. And you can now see that we're already up to that point where we have our baselines, our reference materials, and our scan lines. There are a couple of other secondary reference materials, but we're going to ignore those in this case here. Then for the DRS, I just click on the trace elements and say I want to calibrate everything using NIST 610. And I'm not going to bother using internal standards. This is going to be semi-quantitative. And then I'm going to click crunch data. And now that's done. So that's all you need to do to get your data ready to put into imaging. So then down here on the left side, we have the imaging view. And if you click on that, it brings up the imaging interface. Now, I Actually, I'll go through this interface first. So we do have the setup panel that you can hide and close here. We start off in the overview tab, but we also have the detail tab, the data table tab, and the export tab. And for the overview and detail tabs, we also have this inspect this inspect panel over here, the inspector panel. So we're going to keep that closed for the time being. But to actually create your images, you do that in the overview tab, and here in the setup panel over here, you can see that in the middle part here, in the main area, it's got 3 checkboxes. These are the 3 pieces of information that iolite needs to create images for you. So it needs to know what type of map we're doing. So in this case, this was the type map, so it's from selections. So I just click that button. Then it wants to know which selection group to use. And the reason for this is that you might have a bunch of different images from different areas of your sample measured within the one session. You don't have to plot all of them at once. If you put them in different selection groups, then you can plot each one individually. And so it's just asking which selection group do you want to look at first. So this time we're going to look at the TTN map, the type map, and then, so you can see these are now checked, and then it wants to know what channels we want to plot. Most often you want to plot your output channels. So you can just hover over output, and then down the bottom here, there's this toggle all button. And you can see that it's now created all those images. And it's a fair bit quicker than in iolite 3. And also, unlike iolite 3, it's all done through the one interface. So if it's CellSpace or from selections, it's all one now. So as I mentioned, we have the setup panel, which you can show and hide. We have the different tabs, and we have the inspectors. Just to give you a brief overview of the different tabs, there's the overview tab, which is where we create the images. It's where you can view all the channels at once. You can set global parameters like the height and width and rotation here. And you can also import external images from the overview tab. The detail tab, as it sounds, it's where you view an individual image in more detail. And the data table tab is where you can view statistical information about different regions of interest or profiles in a table format, which you can then easily copy out, put into, say, Excel or into a different program. And then we have the export tab, which is where you can batch save everything at once. So as I mentioned, there's just 3 pieces of information that you need to create the images, which is the image type or the map type, the selection group, and the channels. So once we have created these created images, then I'm just going to put this down because Zoom keeps covering it. We then have what's basically a list of images over here. So you can select them individually by clicking on them. You can select all of them by clicking this button up here in the top left. So if you want to perform some sort of transform on everything, you can select everything and select it. You can deselect everything using this button. And you can actually remove images. So if there's images, if you have a bunch of channels that are just noise, they'll be taking up space in your user interface. They might be taking up memory. So you can actually click on those and just remove them using this button here. If you have lots of channels, say for example using a TOF, you can search for images here as well by their name. So that's these little overview images here. When you're creating the images over here, if you're doing it from selections, you do have some other options here. So there's these alignment options. So just to show what they look like. Your scan lines may not all have the exact same number of data points in them. This is because if you, say, set up a scan line that goes for 30 seconds, you might get a different number of scans depending on where you are in the scan cycle compared to the next 30 seconds. And normally you don't see this unless you have very short scan lines where you might go from, say, 10 scans through to 9, and you can actually start to see these edges. But in case if that is the case, you can choose how you want to align them. So you can have them left aligned, so all the scan lines are aligned on the left. You can align them so their centers are aligned or they're right aligned, or you can click justified, in which case it'll interpolate the data so that they all have the same, every scan line has the same number of data points as the longest scan line. So that's the justified option there. And yeah, as I mentioned, you probably won't see that unless you have very short scan lines. You can also set the map style, so whether or not you've been scanning all in the one direction, which we'd call raster style, or bostrapedron, which is where you scan in one direction and then come back for the next scan line going the other way. And you can see what that looks like. The effect of these, if you were to do this, you can see that it switches every second scan line. This one was measured as a raster, so it makes more sense and it looks better if you go with raster. Changing these has pretty much no effect, no obvious effect in this case. For the meteorite sample that we've included in the example data, it was a CellSpace image, but just by coincidence, all the scan lines do align in their center. So if you do it from selections and select alignment center, then it'll work. You can also switch which direction the scan lines were measured in as well. So they're the options for doing it by from selections if it's that type of map. If you're doing CellSpace, you don't have those options because iolite will know which way you were going and where you were from the laser log file. But it does give you this pixel per spot factor that you can adjust, and this just adjusts the resolution of the underlying pixel grid. So a very coarse grid would look something like this, but you could actually double the number of pixels per spot so that you'd have a much finer grid underlying it. And as I mentioned before, that does have implications for the number of pixels per, the statistics. You can set the shape and orientation of, sorry, I'm just going to go back to highlight. So you can set the orientation, the height and width. So if, for example, our image was more elongated in the height direction, we could change these values so that it more faithfully represents our measured area. I'm just going to take that back to 500. So if you don't have a log file, this can be really handy. Otherwise, it'll use those values from the log file. You can adjust the aspect ratio. If it was a very long skinny, it was supposed to be 1.3, ended up being 13. You can adjust the size of the previews, so you can zoom in and out using this size slider here. You can also adjust the rotation if it's set up other than straight X, Y. You can mirror it in the vertical sense and in the horizontal sense. So all these here are helping you to make the image that you see more faithfully represent the actual sample if you're not using CellSpace images. So that's all the size and orientation side of things. Now we can look at some of the color parameters. So in here we have mostly the color parameters. And the way they work is they work off these color tables, also called gradients. They're now called gradients in iolite 4. And all it does is it takes a map value and gives it a color. And it gives you some choices between linear relationship between concentration and color, log, or ECDF. So this is an image from Rittner and Muller from 2012 that demonstrates this principle quite well. So if you're looking at their strontium image, it's got a histogram of the pixels for the different values. So we have some background pixels which are down around 0, maybe 0 to 25-ish. Most of their pixels are in this, around 200 range, and they have a few that are right up near here at 400. And so if we were to use a linear gradient for this, we can see the lowest value gets the lowest color. In this case, it's a rainbow gradient. So the lowest values would be assigned to blue colors, and then the highest colors would be assigned this reddy orange color at the top here. But the problem with this is that from here to, let's say, this sort of shoulder region here, where we have a few outliers but not much, we probably have less than 10% of our data, we're using up all this resolution here. So from oranges right through to reds, which are basically only going to be used for a few pixels. And the same thing down here in this gap between the baselines and the main bulk of data, we're using up all of our aqua through to green values where we don't have any values at all. So we'd mostly see blues and we'd mostly see some greens, and we wouldn't be using any of the other colors. One way to deal with this is to use a logarithmic gradient. And what this does is in this case, it would actually give us a lot better contrast for our baselines because the contrast is the steepness of this line. So even just across this small area here, we go from blue right through to the green. So we get quite a bit of contrast here, but then everything else is, for all the rest of our data range, is between this green and red. So there's not a whole lot of difference between, say, the peak of our values here at about 200 right through to 400 is all going to be compressed into this orange to red range. So it's not going to give us great contrast either. So Rittner and Muller use this ECDF approach, which is basically a cumulative distribution function. It just adds up the pixels as it's increasing in concentration. And the effect that this has is it means that where there are a lot of pixels, so here in the baseline, that the gradient is quite sharp, so you get good resolution here. In this gap between the two, there are relatively fewer pixels, so this line is flatter, so we don't use up as much of our color scale. And then where we have the bulk of our data, we have a nice steep gradient, and that uses the maximum amount of colors here. And then where it flattens out with outliers, we're not using too many colors. So all of those are available in iolite, 4. So you can see those options here. So you can choose what colors you use from grayscale, which just uses black as the lowest color and white as the highest color. I like jet, but there's all these different options here. And you can choose here what type it is. So you can use linear, or you can use logarithmic, and you can use an ECDF. So the problem with the ECDF is that it can be quite hard to say, oh, this color equals this concentration, because it's not a linear relationship. So it makes it a little bit trickier. Another concept in this is the idea of limits. So the limits are just where the color gradient starts and ends. So if we use this here, we would be using a lot of our gradient in these upper regions here. That's not really useful. So what we can do is we can set a low limit. So a low limit is just a value that everything equal to or less than that is set to the first color. So in this case, if we set the value at about, say, 140-ish, everything of that value or less would be set to blue. And then we have an upper limit, which is exactly the same, but opposite. So in this case, everything that was equal to or greater than 320 would be set to the first color. And so that gives us, a quite steep gradient over the concentrations that we're actually interested in. So to see an example of that, let's look at the lead 206 image. So if you've been following along and created the images, feel free to play around with this as well. So we'll go down to the lead 206 image. And what we can see in this image here, hopefully you can see that image. So if we go down to lead 206 and we click on it, so it's got some check mark, we can see that it basically looks like a dark red triangle. And we've just got, dark red square. And we've just got a little bit of blue here and a little bit of green here. And the reason for that is that there's a couple of outliers here in lead that are completely ruining the color scale. If we look over here in the parameters side, it will actually tell you that the lowest value in the image is minus 0.4 ppm, and the highest value in the image is about 120,000 ppm. So obviously something strange has happened in these background areas, and that is what is completely blowing out our color scale. iolite does give you some options to use these auto values, which will just go to the highest and lowest values, but you can also use this 2SD of the mean. So it will set it to the mean pixel, it will calculate the mean pixel concentration, and then it'll set the lower limit to 2SD below that. And if we click that, you can see that in this case, because we have such a skewed distribution, that's not going to make much sense for the lower limit. But if we do it for the upper limit, you can see that we can start to see some values. I'm going to set this back to auto, and we can also just type in our own values here. So later on, we'll see how you can get the histogram for any image, and you can, if we were to do that, it would look, for this image, it would look like this. So we have most of our values, which probably baselines less than about 100 ppm. Then we have a whole bunch of values around about 250, and then everything's pretty much gone by the time you get to about 750 ppm. So if we were to click on this and say 750 is about the last value that we're interested in, and you can see now that we've gone from what was basically a red square to actually being able to see all our details. So that's how limits work. You can also put little scale bars on your images for creating final images. You can choose where they are, and you can choose what color they are as well. I'm going to leave them off just for the time being. The other thing to look at in this is filters, and we'll come back to them at the end because they're a little bit more advanced. But the other thing we can do here is we can import external images. And I'm just going to switch to the otolith example because that's a CellSpace example, which will illustrate better this idea of bringing in external images. So I'm going to go to open the session. I'm not going to save that one. And I'm going to go to the otolith example and otolith.io4. So as I said, this was set up so that we have a couple of NIST 612 in this case runs. We have 3 in this case, and then we have a bunch of scan lines. And you can see the scan lines at the start and at the end are very, very short in time. So you can see they're quite short there. But when we run that one, so I'm just going to use NIST 612 for everything. And in this case, I'm going to use internal standards. So I'm going to set everything to use calcium. And then for all the otolith selections, I'm going to say the value is 40.04. And that should be enough info to crunch. Okay, now we have all our results. So this time I'm going to tell it that it's a CellSpace image and that we're using the otolith selection group, and we want to plot all of our outputs. And so you can see here straight away, we can see that there's something interesting going on with barium and strontium potentially, whereas the lead, uranium, thorium doesn't seem to be doing much interesting. But what we wanted to show here was this importing external images. So down here at the bottom, if you can't see it, you might need to scroll this panel, but you can click on this import button, and what it will do is ask you to import your external image. Now, for registered images, they have this underscore mapped file name. So it's whatever the original image name was, and then underscore mapped. And they should have this another file within the same folder with this .coord file extension. And if iolite can find that .coord file, it'll use that. Otherwise, you'll have to manually register it. So if we click on open, it will show this window here. And this window allows you to plot your laser ablation data, and you can change the opacity here. So you can, from one where you can see the external image 100% to seeing the laser ablation 100%. And we want to be somewhere in between the two. And because we're using the .coord file in this case, it found it. You can see it's got this, it's highlighted up here. Then you can see it's done a great job of aligning the data, which makes sense. But if we didn't have one of those, we could also do it via manual transformation. So where we would set the scales, so about say 0.6 and about 0.6 in horizontal and Y. You can also grab the image and drag it relative to the laser ablation data. If there was some rotation, you could apply it here. So you can do it that way to line up your images. Obviously, it's much more difficult and less precise. You can also use a 3-point transformation. If you click on 3-point transformation, and the way this works is that you select 3 points and you tell iolite where they are in your laser ablation data and where they are on your image, and it will map one to the other. So for example, if we were to say for point 1 in the laser data, it's about here, and on the external image, it's about here. So these points are about equivalent. We'll repeat that for another one. Let's say we'll use this part here. These are about equivalent. And do a third point. Just say this is, and these are about roughly the same here. And then we can click this test button up here, and it'll show that they're overlapped. It'll show how well they're aligned. Obviously, you want to spend a bit more time doing it than I have just there, but that's how you can bring in external images even without a .coord file here. But we're going to use the .coord file because, as I said, it's much more accurate. Click on OK. It'll ask us for a name. I'm going to call it a photo because that's what it is. But you could be bringing in an external image that is like, say, an SEM image, or a cathode luminescence image, or just a scan from a scanner, something like that. And all of those things can give you more context for your images. The other thing is that you can, if you click on it, you can actually change what is an RGB image, so it has red, green, blue color channels, to a grayscale image, and then use that just like a channel, just like your other channels like these here. So then you can use that in things like selecting data. So you could select parts of your image by grayscale, and you can actually create regions of interest that way. For the time being, I'm just going to leave it as normal. And now you can see that we have our laser ablation data and our external images. We can also, in this view, we can also use the pointer overlay. And what this does is it allows us to hover over any image, and it will tell us in all our other images where our mouse is hovering. So if, for example, you have, excuse me, if you have an anomaly like this little part down here, you can hover over it and see if there are anomalies in other channels. In this case, we don't have any of that, so it's not a great example, but you can also use it to hover over things like this. So in our external image, you might see that there's this track running up here. This was a profile that we did before we measured all the other elements. And you could actually hover over that to see if it comes up in any of the other images, and you can see that it doesn't show up. So that's the pointer overlay. I'll just go back to this to make sure I haven't missed anything. You can also see where your external image fits in with your data. If you click on your external image and say show external image, and it'll show you where your laser ablation data plots over top of that. Overlay. Excuse me. Okay, so now that covers pretty much everything in the overview tab. So as I mentioned, this is where you create your images, and you can see all of your images at once. So you get a good feeling for all of your different channels. Then we might want to start creating or looking at individual channels in more detail and perhaps creating some graphics that we might want to use for publication. So we can click on this detail button, and when we click on that, we have this setup panel again. It's different this time. There's 4 different tabs across here. There's the 2D tab, RGB, stack, and 3D tab. So the 2D tab is, as it sounds, it's just where you can look at an individual image in 2D in more detail. So if you were to click on, say, strontium, and it brings up the strontium image in the main part of the window. And if you click on this button up the top here, you can zoom to full extents. If you hold down the Command key on Mac, Control key on PC, on Windows, and scroll your mouse scroll wheel, you can zoom in and out to zoom in to certain features, so you can zoom right in. And as I mentioned at the start, you can actually see that we've used a round spot because you can see the edges of each of these tracks are curved. That's where you're actually seeing each individual circular spot being plotted, or rather each individual mass spectrometer measurement being plotted as a circle for its sampling area. So the same thing here, you can set the different color gradients. You can change the color limits. I'm going to change this to between 0 and I think 6,000. So that gives us pretty good contrast. If I use the ECDF in this case, it does give slightly better contrast. It's pretty linear actually in this case. We did have a question in last webinar about using percentiles for coloring, and that's effectively what the ECDF does. But we can get into that in more detail later. If I wanted to save this image out, I could just click what image type I want to save. So if I want to save a PDF, just click that, and it's going to save that image that we see as a PDF. We can include the scale, the color scale, either on top of the image or as a separate file. So if I was to say that it's, say, a PNG, and I'll just put it, so I'm going to call this export 1. And if I was to go to that, that file, I have put that in the wrong place, I think. So now you can see it saved the scale bar here and as a separate file, and it saved the main image here. So you can load that into other graphics programs, or you can use that as it is. And then you can go back and forth between your different images using these buttons. So here's barium. I'm going to keep using that, but I'm going to decrease the limits to, say, between that and A100. And let's look at one other as well. Let's say magnesium, and we'll see if ECDF does a good job of that one. Interesting. So that's what the detail tab does for you. This is an example where the ECDF doesn't it maximizes contrast, but it doesn't necessarily make an easily understandable color scale. So you can see the color scale over here. If you're looking at the green parts of this image, it's very difficult to tell whether it's, say, 1,000 or 8,000. So actually, let's skip back to, say, logarithmic. Okay, so that's the 2D tab. If we were to click on the RGB tab, this is where you can create a false color image where the red intensity, the blue intensity, and the green intensity are all defined by 3 separate channels. So just as an example, I could set the red up to be, say, strontium, the barium to be blue, and the magnesium to be the green. And what you see here is that where we have almost pure blue, that means it's high in barium and not the other 2 channels. Where it's red, it means that it's high in strontium and not magnesium or barium. And where it's green, there's one spot there, I think, that shows that. it means that it's high in magnesium but not in barium or strontium. And where it's white is where you have it's high in all three elements. So that's one way of displaying three channels at once. So it does present more information in a single image. And it does get its values there it does get the color limits from the 2D tab. And same thing, you can save it out by clicking any of these buttons here. If we go to the stacked tab, this allows you to stack your images and adjust their opacity. So if, for example, I was to put the external image on the bottom, and then I will put my strontium image over the top, let's zoom out a little so we can see. And what we can actually do is we can adjust the opacity as we like. We can add other channels to these. So if we barium over the top, we can adjust its opacity. You can change the ordering of these. So basically you can build up an image with as many channels as you like, with different opacities to show the features that you want to show. Same thing again, you can save these out down here. And the final of these tabs is the 3D tab. So with the 3D tab, it creates a colored surface, and you can choose the height of the surface using a particular channel. So for simplicity, we're going to choose strontium, and the color of that surface is set by another channel. In this case, I'm going to use the same channel for both. And what that does is it creates a 3D image. By default, it has a mesh over the top of it. So we're going to turn that off. If you click and drag the image, you can move around it. If you hold down the Shift key and move the mouse scroll wheel, it adjusts the vertical exaggeration. And if you hold down the Command key or the Control key on Windows, it will zoom in and out. So you can adjust this so that you can see the best angle that displays the features that you're trying to represent. I'm going to actually just show what happens if we use a different color for the coloring. So you can see here, it's all blown out by this little bit on the end here. I'm actually just going to go back to the DRS and not use internal standards. Just punch the data. Then we go back to our imaging. And I'm going to have to start that again. So CellSpace, Otolith, and all my output channels. Okay, so as you can see, it doesn't take long to go back and recalculate everything. But what it's done is it's got rid of these parts on the end here, which were blown out by some abnormal calcium values. If we were to go back to the 3D tab now and select, say, strontium as our height and barium as our color. So you can see here in this case, it's actually the lighter colors lower in strontium. So all the light colors are in the low parts of it. So that way, again, you can show information from two different channels in one image. And in this case, it's a surface image so that you can really get a feel for the troughs and the valleys. And again, you can save this out by clicking down here. So that's the different the different tabs in the detail view. And I think that's most of what I wanted to show you there. Okay. So now that we've created images and we've saved some out, we can actually start doing some proper image analysis. And this is where the real power of iolite comes in. So the image analysis tools in iolite 4 are based on the monocle add-on for iolite 3 that Joe wrote. And it allows us to do more than just say what's high and what's low. Because that's basically the first thing that you do is the eye jumps to what's high and what's low, but it's not long after that before we want to know a bit more. So the way image analysis works in iolite 4 is that we have a series of image inspectors, and these display information about pixels within a region of the image. So the most basic is the stats, and it will report the average plus or minus the 2SE of pixels within a particular region. But these inspectors are all fully customizable. You don't just have to use the ones that we've provided, and you can change the settings for the ones we have provided. You can change them to plot what you want to plot. They can be really simple, as the stats one is, which just is plotting the reporting the average and the 2SE, through to things like Concordia diagrams or rare earth normalized plots. As I mentioned, that comes with 8 built in, so that's those there on the right hand side. But even more powerfully is that you can write your own. So you can use Python to write these inspectors, and you can take advantage of all the libraries that are in Python. So things like, you know, machine learning or all the neat things like cluster analysis and those sorts of things. So once again, as we've always said with iolite, it's not supposed to be just about our ideas. It's about hopefully giving you the tools to enable you to create your own tools. And so that's what these inspectors are really good at. You can, with any of these inspectors, you can pop them out to become their own separate window, or you can dock them again so that they sit within the inspector panel. As I mentioned, there's these 8 that come with it by default. So there's the density one, which will give you a KDE for the region of interest. There's a histogram one. There's a rare earth plot one. There's one that plots just the raw data points within the area that you've selected. There's one that gives the mean and the 2SE. There's a weather or Concordia plot. There's an XY stats plot and the XYZ. So XY stats is the same as the stats plot, but it's in 2D, and XYZ is the same, but it's in 3D, with the color being the third channel. So as I've mentioned a couple of times, there's this idea for any statistical analysis of pixels, you need to take into account of n measurements. And for CellSpace, we can't just necessarily use the number of pixels, because we might have changed the number of, well, it's not just one pixel per mass spectrometer measurement, it's some arbitrary number. Instead, what iolite 4 does is it will create a mask for the time resolved mass spectrometer measurements. So let's say that we had a rectangular region that we were looking at, that we wanted to get stats for in our image, and it was between x equals 100 to 200 and y was between 50 and 150. And if we look at that as a table, what we would have in our time series data is we'd have our time values, obviously, and we'd have our y position, so x positions and our y positions and our compositions for each of those. And what it would actually do is it would look for any values that are within the x range and any values that are within the y range. So it actually highlight these values here. So it would give you the stats for these here. So it's not actually looking at necessarily looking at the actual pixels. It's going back to the original mass spectrometer measurements, which is really important and actually gives you proper stats. So that's a key part of one of the advantages of this iolite 4 approach. So let's do some image analysis. Before we get into it too much, we need to work out what we talk about when we talk about a region of interest. A region of interest is really just a sub-region of your image that you want to get some more information about. They can be polygons defined by XY coordinates. They can be more complexly defined. There are also the loop that you can run over your image, and we can also create profiles, but both of those are really just special cases of a region of interest. So the loop, which is just the area under the mouse cursor, is the most simple. And that's probably the one that you would start with if you're doing some image analysis. So let's go back to the 2D view, and we'll have a look at, say, strontium. And when we want to do some image analysis, we pop open the inspector panel. It's this one on the right-hand side here. And you can see that we've got 3 different tabs up the top. We've got loop, region of interest, and profile. If we click on the loop, you can see that there's this little circle that follows underneath our mouse cursor here. And at the moment when we're moving around, we're not seeing anything here because we haven't added an inspector. So these are these built-in and customizable inspectors that I was talking about. So let's just do a histogram because that's nice and easy for people to understand what's going on. And for our histogram, we don't necessarily have to have a histogram of what we're looking at currently. We can actually select our area using a different image and look at a histogram from a different image. But we're going to look at strontium-88. And you can see as we move over our different areas, we're getting a histogram. I'm just going to make this a little bit bigger so that we get more pixels. And I'm going to switch it to a rectangular, square in this case. So you can see now, as I move over the different parts of the image, that we get a histogram of it. And it doesn't take long before you can see things like this, where we've got some sort of bimodal distribution in our histogram. We can also add another inspector. Let's say, let's just do stats. It's nice and simple. And it will give you the stats plus or minus 2 SE. For the loop, that one doesn't make as much sense. So we can actually close them using these little buttons here. So we can undock them with this, and we can change the size of them here. But we're going to close this one. And so this is the loop, basically. We can also make it more elongate. And we can actually, if we had, say, growth layers that we wanted to follow along with our mouse, we can change the rotation of it. This doesn't have growth layers that we can easily follow with the loop, so that doesn't make sense in this case. But you can make that loop to any shape that you want. Well, not any shape, a rotated rectangle or a circle. This is a great way to get a feel for how high is high. So in this area here, if I was to make this back to being 100 by 100, and I was looking in here, well, now I can see that it's roughly, on average, just the average of these pixels here is a little bit less than 6,000, plus or minus about 1,000. And if I was to go into these blue areas, well, how low are they? Well, they're down to about, say, 1,500, but there's a lot more variation there. Actually, no, it's not a lot more variation. So this is a really good first pass at looking at your data. But as you can see, as soon as I move my mouse, I lose that region that I was looking at, and so my stats change. So the next level of analysis is to start talking about regions of interest. So if we click on this, we will see here that we've got a list here where when we start adding regions of interest, we'll start building up a list here. So the easiest way to create a region of interest is to click on this add button, and we're going to draw out an area. So if you click add, and then down the bottom here, it will say click on an image to add the first vertex. So if we start clicking, I'm going to just highlight this central high region here. This is the core of the otolith. And I'm going to define the region of interest by adding a bunch of vertices. And the trick with this is that when you want to finish up your region of interest, you just double click, and that will say this is the last vertex. So I'm just going to double click. And then once I do that, I'm going to call this ROI1. Doesn't matter what you call it, just want to call it something that you will be able to remember. And you can then see that we now have a region of interest here added in our list. And then when we click on that, you can see that the inspector is now giving us the stats for that. So we could then, so then we don't have to memorize where our mouse was. We can start drawing regions of interest. Let's add some more. Let's say draw one out over here, just so we can see what happens when we have multiple. I'm going to call this ROI2. Let's add another one down here. Call that ROI3. We'll add just one of these ones in here as well. Obviously, if you were doing this for real, you'd probably potentially give them better names, like core for this first one, or rim, or low area, or something. Once you've created them, you can also go back and edit them by clicking the edit button up here. And then you can grab these points and edit them. If you want to delete them, you can click the remove button here. And you can see now that we have a bunch of them. If we click on each region of interest, it gives us the stats for that. Now we can actually start looking at some of the other inspectors. So let's put on raw. And what we can do here is it's going to plot all the mass spectrometer measurements that have XY positions within the range defined by this region of interest. So we're going to switch to, say, strontium versus barium. And you can see as we move between these, you can see that it's showing us all the raw data there. And even better is if we select all of them at once, you can actually see that they all plot at once. We can see all the histograms at once. We can look at the XY stats for this. Actually, what I'm going to do is I'm going to just pop this one out. I'm going to undock this one so that we can have it a bit larger. And so now we've got room for this one here. So we're going to say for this one, the x-axis is going to be the strontium, the y-axis is going to be barium, and we'll use magnesium ppm for the color. So you can change what color scale you want. So if we go to hot, so darkest will be dark color. So the lowest magnesium values will be black, and the highest will be yellow. So you can also right-click on that and save that as a figure if you want. We could close that, and we'll add just a plain stats one. So you can see here it's giving us the mean plus minus 2 SE for each of those. And as I said, we can create our own inspectors as well. So you can use some of the Python ones, the existing Python ones, as templates. So if you go to Python, I've already started making Python ones on my own here. But if you click on add, it'll ask you to give it a name. So I'm just going to call this test 2. And you can use one of the existing ones as a template. So let's use the density one and click OK. And then if we were to show that inspector, I'm just going to close this one so we can actually see it. So you can see it's plotting the KDE of our different regions over here. And that's because we use the density inspector as our template. But if I was to click on this edit button over here, you can see all the code that's used to create that. And most of the code is actually in the settings, setting up the settings. This is the part that is actually calculating most of the results for us. And I could actually go in there and change that to be whatever I like. So that's really powerful in that it allows you to, as we said earlier, take advantage of all the scientific libraries, computing libraries for Python. You can also use these for the loop as well. So as you pass over different areas, it'll give you the KDE for the particular area that you're looking. So it'll give a live update, which actually looks quite cool for when you're looking at the raw values. So if I'm not plotting one-to-one. So you can see that it'll show when we go over the baseline and the higher values, it'll show those. But so that's the basics of the regions of interest and the loop and the inspectors. When we get to profiles, a profile is really just a type of region of interest. So to demonstrate that, we're just going to add a profile. It's the same thing. You draw vertices to define the profile. So click once to start it. And then I'm just going to add one that followed that original track that we could see before. And double click when you get to the end. And I'm going to call this profile 1. And click OK. And what you can see for the profile is that the profile doesn't just measure the pixels that are underneath it, because what if you clip a pixel, does that get included or does it get ignored? What it actually does is it allows you to select an area perpendicular to the profile. So you can see these regions here. Each one of these is a slice. So the profile is actually made up of a bunch of slices. And you can actually adjust how big the slices are. So if we were to make them, say, 25 by 100, and now you can see that we have a lot more slices, and it would actually give us a lot more resolution. So let's close these, and let's add an XY, and not XY. Excuse me. Let's add just a stats inspector. So you can see that and you can change the channel that you're looking at again. So you can see here that the profile starts here in this high region, then moves to the low region. So you can see that here. You can actually even see this little bit of a lump here, this little curve here, which is this region through here. And then it goes back up to the high values before it drops back down to baseline values. So that's that's profiles. You can adjust. So if we wanted to make these, if we wanted to have less resolution, you can see now that we have fewer slices, but we have much better stats for each one because each one includes more mass spectrometer data points. So you can make that trade-off. You can adjust your profiles to have more pixels, so less uncertainty, or you can have more resolution. So that's, and the profiles can be as complicated as you like. As we did here, we've just done a reasonably simple one, but they can be in any shape that you like. They don't just have to be between 2 points. Excuse me. So that, you can also, up here, you can edit these, you can remove them. You can show the profile here, which does a similar job to this stats one, but you can show multiple at once. So if we want to put, say, strontium and barium there, they're different orders of magnitude, so we'll make it a log scale, and you can use that as well. You can show and hide that there. And you can have multiple profiles as well. So we have our regions of interest with all their information there. We have our loop and we have our profiles. All of this information is collected in the data table. So in the data table, you can see we have our regions of information, regions of interest. And for each region of interest, it will tell us the area that it occupies, how many points are within that region, what type of region of interest it is, and then it would give us for each channel the mean and 2SE. So this is really handy for being able to get for a particular region a representative value. Same thing with profiles. You can, because each slice in the profile, you can actually get a value for that. But if I was to limit this to just being profiles, so we can filter up top here by typing in values. So now I'm only showing, it's only showing regions of interest that have prof in their name. So it's only showing the profile values. And I could actually copy out all the values here and plot them in, say, Excel or something like that. And we have the uncertainty for each one, so we could also add error bars to each one there. You can also right-click on this and just say Save to Excel or Save to CSV. Similarly, we could also, if we don't want to see everything, we could just say, just show me the magnesium, any channels that have magnesium in them as well. At the beginning there, I did kind of skip over the channels part. You don't have to just plot output channels. You can also plot intermediate channels or even input channels. So that's all entirely possible as well. And now we will look at, so you can, yeah, you can save information about your regions of interest from this table here, this data table. And at this point, you're probably interested in saving out all your results. So we can just use the export tab here. We can set the base name for each image. So for example, if I was to use otolith, it would save otolith _ strontium ppm. And then to do the same thing for the barium would be otolith _ barium, otolith _ uranium, whatever. You can set what folder it's going to save them into. So let's just pop them in here. I'm just going to call this my export folder. And I'm going to select that. So now when we do our batch export, all of our images will end up there. We can choose what type, what format our images are. And if we save out our data table, we can choose what format that's in. So this, we can save out a copy of this data table in Excel or CSV or tab separated values. You can choose whether or not you want to include an overview image, which shows all of your images at once, whether or not you want to, or you normally want to save out all your individual images. It will save some metadata about your images. You can also plot your regions of interest so you remember where each one was. It will plot out one of those and you can say what image you want it plotted over the top of. So in this case, we'll just stick with the photomicrograph. The same thing with the profiles. We're going to have that plotted over top of our photomicrograph so we can remember where our profiles were. And we do want to save out our data table. You can also, for further analysis, you can actually save out the matrices, the matrix of image values as separate files that you could then potentially load into other programs, like say into ImageJ or some other statistical package to do more stats on your particular images. And same thing with the individual regions of interest. So if I wanted to take all the data from, say, this core region here and this value here, and I wanted to do some statistical analysis on it, I could actually export all the pixels, or actually all the mass spectrometer measurements that are within this region as another matrix of values. So you can do more analysis on those. If you do save out those, just be aware that it will probably go very slowly because saving these out can be quite slow if you have a lot of images with a lot of data points. You can set this up as your default so that you don't have to change the image format type and set these individually each time. But when we click on export, it will start exporting our images for us and it's all done. And now if I go to that folder, you can see in here it's created an image for each channel and its color scale. And it's also saved out the data table for us. It's also got some metadata. So in this case, we just have the dimensions and the spot size. And it's saved our overview for us. So here's our overview image. And this on here, this is showing our profile plotted over the top of our photomicrograph, so we remember where our profile was. The same thing with the regions of interest, so it's showing us where our regions of interest were. So that's really important. If you come back to this later on, you want to know what region was chosen. And it also gives you some references to cite as well. So that's the output side of things. The only things that I haven't covered in more detail is, so I skipped over a couple of things there, but some more advanced things that you can do are, you don't just have to create regions of interest using polygons, drawn polygons. You can actually use some other more advanced techniques. So if I was to click and hold on this add button, you can see that polygon is the default one. That's one where you draw your area. but there's also this from seed and from criteria option here. So if I was to choose this from criteria as an example, and I wanted to select, say, high, I would say lowish strontium. This is just like the automatic selections from channel data that you may have come across in the basics. So if I click on add here, we can add some criteria here. So for our simple one, let's say we want to select where strontium is in the range from, let's say, from 500 to 1500. And I'm going to call this mid strontium, and click OK. And then when I click on that, you'll see that it's selected all the values that fall within that range. I think I may have been a little bit tight there, but I'm just going to switch the color to black so you can see to grayscale. So you can see in red, it's picked up all these values. I might actually go back and edit that to be a little bit more permissive. And now you can see it's selected all the mid-range strontium values. So that's like that's a really powerful way to create regions of interest using set criteria. And you don't just have to set it based on one channel. We could add more channels. So I could say where barium equals a certain value and so forth. So that allows you to be really specific with your regions of interest. Another way of doing it, and I'm just going to switch to the tight map for this, just, I think I had a bit better example there. Can I ignore that one? So this is from selections, tight map, and output. So I was looking at the terbium map here, and if I was to go into detail, look at that. Now, say I wanted to select one of these regions here, this darker core here. I could create my region of interest using a seed. So if we click this, if we go to region of interest, click add, and so we click and hold it, and go from seed, and it'll say, where do you want the seed to grow from? So basically what this does is you select an area and it will start to expand that area until it crosses some threshold. It'll grow from that seed based on a bunch of settings that you can set for it. So I'm going to say, let's start growing from in the middle of this this area here. So I'm going to change, so and it'll bring up this window here, and we're going to say, let's view terbium, and we're going to base it up here. So you can set where the seed is, what it looks like. We're going to add a growth policy based on terbium, and we're just going to auto grow that. And you can see it's automatically expanding out until it gets to the edge of what it thinks is a different region of interest. And we can now call this sort of flow terbium. And we can click save. And now we have this region of interest that has automatically grown. So I just used very basic quick settings there, but you can see that that's one way of creating regions of interest very quickly and using sort of a smart algorithm approach to it. The other thing that I haven't covered yet, and I want to leave some time for some questions as well at the end, is filters. So I do have a little bit in the presentation on filters. So export tab, filters. So iolite does come with some filters that you can apply to the images. You can apply them and remove them so they don't change the underlying image data. It's something that's done subsequent. There's a bunch of smoothing ones, so you can smooth in 2D, or you can just smooth in one direction, columns or rows. You can smooth in a Gaussian sense. You can also expand the number of points, so you can basically do interpolation. So this can be really handy if you have very high resolution in one direction but not in another. You can interpolate between rows and columns. You can also do some masking. So I'll just quickly show some of those. Let's get rid of our region of interest. If I was to apply a filter this, you can choose here what filter type. So if I was to apply a box filter, you can see it does a lot of smoothing. If I click on it, I can actually change the size of the filter, the amount of smoothing that it does in both the Y and the X axis. So if we crank it right down, you can see it does little. We turn it right up, it does a lot of smoothing. We can remove that. If I was to add, say, a Gaussian, we could apply that Gaussian, and it looks quite similar in this case. But the one that I thought was quite nifty is this mask. If we apply a mask filter, what it will do, it's basically a high pass filter or a low pass filter. If you click on it, and you can actually say, show me all the values. So block out all the values that meet these criteria. So again, if I was to say terbium, and let's say less than, let's say, is 100 too much? Yes, 100 is too much, way too much. Let's say less than 50, even less than that. So you can see that what it does is basically it starts to blank out regions of your interest, regions of your image based on values. So that can be really handy. I haven't done a very good job here of getting rid of my background regions, but I could have actually added more criteria to this as well. So that's filters very quickly. So hopefully that covers most of the stuff in the presentation. So yeah, hopefully this gives you a feel for how easy it is to actually create images in iolite 4, and then go beyond that to either use the existing data analysis tools that we've put in or create your own. And there's heaps of scope there for customizing it to your needs. So again, iolite is not set up just for what we do. It hopefully allows you to do any sort of experiment on it, whether it's biological, zoological, mineralogical, etc. I just wanted to point out before we go to the Q&A session that there is documentation at iolite.xyz/docs. The imaging documentation is still being written because we've been adding to it a lot recently. There's also the blog where we write notes on things. And normally it's where we take some concept and we discuss it in a little bit more detail. There is also the forum. So we recommend the forum as being your first point of contact because you might find your answer straight away. So please definitely use it. Also, other people can learn from the questions you post there, but you can also contact us at support@iolite-software.com if you have any problems. So with that, presented, we're quite keen to hear if you have any questions, if you have any feedback for us. So yeah, please you can either ask a question via chat, or you can either unmute your microphone and ask a question that way. Jason had a question about laser log files, saying, are all laser log files compatible with this version of iolite or only modern systems? There is a standard format for the log files. It's been standard for a while, but there were some of the companies had some bugs with their log files. But basically, yes, it should be able to handle any log file as long as it's got the information in the correct format. If you're having trouble with log files, please get in contact with us and we'll let you know if there's anything we can do about it. or maybe we can speak with the laser company and see if we can work something out with them as well. Mingli has a question about, can you do a ratio map? Yeah, so one way to do that through the interface is, if we wanted to create our own ratio, we could go to the calculator. So if I wanted to make, say, we've been talking about strontium all day, let's call it strontium to barium channel. So we'd say strontium 88 underscore ppm divided by barium 138 underscore ppm. We call that an output channel, and we click calculate. Now we can see in the state that it's click plus. If we were doing this regularly, we could save this channel as well, but it's just a demonstration. And now when we go to imaging and in the overview, in our output channels, we have a strontium to barium channel. And there you can see. So reasonably quick. Yeah, so Frederick has asked a question similar to that. So creating a region of interest from ratios. So I just created a ratio image, and then I could use that in the region of interest from criteria, and I could say select strontium to barium is, say, greater than, I don't know, 1, and call this high strontium to barium. And it looks like just about everything is high strontium to barium, but you get the idea. Actually, I'll just see if I can adjust that to something. Where's some place where it is 100 to 1? Okay, so there you go. That's where you can see that the strontium is 100 times higher than barium in these regions here. So Dave asked a question saying, I saw that you can plot spatial data using a linear or log scale. Can you plot as percentiles? It is an approach that has been used for field mapping of geochem data, and I've always found it very useful. Not at the moment, but that's a good suggestion. I feel like the ECDF would do that to some extent. So it'd be worth having a look to see if it works for you. But if it doesn't, yeah, it's an interesting idea. We'll look into that some more, I think. It's a good idea. Okay, Simon agrees as well. That's a good idea. Yeah, I think that's a good idea. We'll look into that a bit more. I think that if we can do the empirical cumulative distribution function, it shouldn't be too much harder to do percentiles, because we're already looking at, basically the cumulative distribution. All right, yeah, we have time now. So let's talk about the filtering. And the custom one, if I just show that just very quickly, if you click on that, it allows you to actually type in your own kernel that is convolved with your image. So we'll be adding a few different ones, like some sharpening ones and maybe some edge finders, those sorts of things. So this is by default a sharpen kernel, Joe's telling me. But you can change the size of that, and you can type in whatever you like. There's this that gives you a lot of freedom right there. So for people who are familiar with those sorts of image convolutions, then it's really quite cool. Thanks to everyone for joining us. As I said, there's the forum if you have any questions, or there's the support email if you want to get in touch. We are working on blog notes all the time to give sort of slightly more information and worked examples of how some of this works. We're expanding the Python API as well. so that you can do even more with this, and it becomes clearer, because as we've always said with iolite 4 and with all of iolite, it shouldn't be about what we think is how you should do things. You should have the freedom to do whatever you want, just using iolite as a platform. So that's one of our guiding principles. So hopefully this gives you some ideas for some of the things that you can do. And yeah, get in touch with us if you have any troubles or need any help. And otherwise, thanks to everyone for joining us, and hopefully we'll see you again sometime soon in the future. Thanks very much, everyone, and we'll see you later.